Limits tends to be a calculus topic approached in pre-calculus. And it's a pretty appropriate one to approach in pre-calculus because we get to spend more time with it and develop the ideas deeper than they're brushed in calculus. So we've talked a little bit in problem 1 about some of the implications and applications that we've seen naturally happen. Some examples that we've looked at are the soccer videos that were buffering and how we had to draw some conclusions based on some observations. We had to make some predictions, right, about what happened. And Archimedes, the Greek mathematician who was trying to approximate pi by inscribing and circumscribing polygons around a circle, and his prediction of what pi should be. Other things are in chemistry. We have the half-life and carbon dating. So the idea here is that elements exist, in this particular case carbon, and that as time goes on, the amount of carbon present, the element carbon present in a substance is going to go ahead and decay. So quite much like exponential decay. However, we'll never ever get to 0%. There will always be some amount of the element left. So again, this idea of a prediction. I mean, it's going to pretty much be 0, but it won't be 0. Newton's law of cooling, this idea that to an object of a higher temperature versus its environment, that object will release heat energy to the environment, and in the process it becomes cooler. So as an object is cooling off in a room, let's say we have a hot bowl of soup and we have it in a room, for all theoretical purposes, what happens is as that soup bowl cools off, it actually warms up the room. And so it is not as simple as, okay, it's going to become one temperature instantly. There's a give and take. And so we make a prediction of what will happen, even though theoretically it wouldn't come to an equilibrium point. And then we looked at population logistic growth and the carrying capacity. Remember when it overshoots and then it compensates and it overshoots and it compensates and it keeps doing that. And we ran a simulation for, I think, 30 to 40 generations and we still didn't see it stabilize. But we could stop the simulation and assume that it was going to stabilize eventually. So we would just make a prediction, even though it may not actually come to pass. So this idea of the limit has always been existent in mathematics and in science, but we haven't really formalized it until now. So let's bring in some math, and here we have a function, and this is a nice feature about Desmo is that it'll graph it for you and it'll also show you the function, and if you click on settings, the little gear, it'll give you the option to add a table. So here's a table, and Desmo does not do a very good job at drawing the hole, right? There should be a hole right here because it's undefined at x equals 2. There should be a hole right here because it's undefined. So if you were to click on the line and actually follow it up and down, it'll actually reveal to you. It'll say here 2 undefined. So we have a hole right there. Okay, and what this means is I could be riding along this freeway, but at some point there's just a city missing. The city is gone. It is not there. It should have been there. It's not there. Okay, or I could have been driving along it this way and expecting to get to a destination, but it's not there anymore. So to show you what we do here, so I typed it into Desmos, right? Make sure you have the f of x notation for the function, and then we go ahead and click on this gear, and I can put this table, and there's my table, which we saw in the notes. Now, this is not really convenient because there's only 5 spots. Okay, so for example, if I want to put the 2 here, I could do that, and I say I want to put 1 here, 0, and 3 and 4. That way you can get a better picture of what's going on. So notice that, you know, it's about predicting, right? So I get 2, 3, weirdness, 5, 6. So what should have this been? If we were playing a game of hide and seek and we were counting, and some kid is like 1, 2, 3 undefined, 5, 6 is like we weren't expecting that, right? We were expecting 4. Okay, so this should be 4. It just is not 4. So let's make this clear about limits. A limit is a prediction. It's not saying what really is reality. Reality is it's undefined. It's not there. Okay. However, we totally are justified and expect that to be 4 because no matter how you count, right? I mean, 1, 2, 3, or what if you count backwards, right? 7, 6, 5. So whether you go this way or this way with the numbers, you're totally expecting the answer to be 4. Okay? That's what a limit is. Now, before we develop this idea even more, well, what if it's not 4? What if it could be, I mean, between 3 and 5, it could be 3.5, right? Or 3.7. So here's what I want to suggest. When you use Desmos, you're going to have to just type these in. But let's say we know that 2 is the issue here, right? We know that 2 is the issue, so we want to lead up to 2. So what if instead I did like 1, and then I did 1.5, and then I did 2.5, and then I did 3. So you see, we're getting a better view of what it should be. Remember the video frames with the soccer buffering video? It's nice that we get the beginning and after frame. But what if we got really close? Like what if we got as close as possible to the millisecond before the buffering happened and immediately after the buffering happened? So that's what's happening. When I change these, right? Let's say I even go crazy, like 1.5, and I do 1.75. Do you see how much closer these are? Like, what if I, just for kicks, what if I put 1.999, right? And I put over here 2.00001. Look at how crazy close this is getting. You see, there's no more room for like, oh, I think it might be something else, right? What's between 3.99999 and 4.00001? I mean, you can't deny there's going to be 4. Now, I know you believed me before when we counted, right? When it was, 2, 3, undefined, 5, 6. It was obvious. But it's important that you recognize how to do this technique because the closer we can get to the buffer, right? This is the buffer. We didn't see this part of the video. The closer we can get to right before it buffered and immediately after it buffered, the easier time that we have in recognizing what exactly happened at this undefined point. So looking back at this, what happens at f of 2? Well, at f of 2, it was undefined. There it is. So looking at these values here, and if we go ahead and put, fill them out using Desmos, we get these values, right? So, it's nice using these big numbers, right? So we can get a better understanding of where this is going. But once I get pretty close to this region right here, right? 3 to 4 is a pretty big gap. And it depends on how you look at it. So we need to start looking at numbers in multiple ways. You might think, okay, well, $3 to $4 is no big deal. But what about 3 billion compared to 4 billion, right? Or 3,000 RPMs versus 4,000 RPMs. There's a difference. Okay, so what happens is the more decimals we put in, we're pretty much trying to really edge ourselves to the point where we can almost pretend that it is 2, right? This is, as far as you're concerned, you would round this up to a 2, even though it's not a 2. Or you would round this up to a 2, even though it's not a 2. So we're getting so dangerously close to this that it's revealing to us very dangerously close what it should be. So we know that 2 is undefined. But if I plug in this value into this function, I'm going to get something like this. If I plug in this value into this function, I'm going to get something like this. And what we're expecting is what's between this and this? Well, a 4. So from the left, right, as we're looking at the x-axis. There's this graph that we had, and this is the x-axis, and this is the y-axis. So on the x-axis, we're going from 0 to 1 to 2, but 2 is undefined. So we're like, well, what if we're inching towards it, right? Like 1.9, 1.99, 1.9999. So from the left, it's approaching 4. If we do the same thing from the right, we're going in this direction, we're approaching 4. So regardless, as long as we're trying to approach this hole at 2, the limit of this function as x approaches 2 equals the number 4. Okay, so what we're saying is, let's make this very, very clear. At x equals 2, this function is undefined. However, the limit as x approaches 2 is 4. A limit is a prediction of what should be there but may not be there. Now, how do I write this? Well, let's go ahead and write this formally. I would write that the limit of x squared minus 4 over x minus 2 as x approaches 2 is equal to 4. But remember, that's different from this. F of 2 is equal to undefined. So this is what you've learned in Algebra 2, Algebra 1, okay, that given a domain of 2, the range in this case is undefined. You plug in a value, it's supposed to spit you one out. So f of 2 is undefined. However, if we took the limit approach, if I plug in a 2, it should be a 4. It's approaching a 4. It's a prediction that it should be 4. It's not 4, it's just a prediction. So this is how we write it, right? Notice how it's written, how it's typed. The function goes right here. The limit as x approaches this value. Okay, and then this is the actual limit itself. And when we do this, it's important that you look from both directions, like you're crossing the sidewalk. You look from the left and you look from the right, and you see what it's approaching on the table. Summary. What is a limit in your own words? How would you describe it to a 5th grader? Good luck.